Welcome, Geometry iPad class students from OHS. This is just going to be a short, informal little video about Chapter 2 for your review assignment. Might help you out on some things. Hopefully it will. I'll try and keep it pretty short, though. First couple of things. I want to talk about some vocab, some important vocab. Let's see, a statement you can prove and then use as a reason in a later proof. Well, a statement that can be proven will turn into a theorem. So theorems are statements that can be proven. Is a property of using logic to draw conclusions from given facts, definitions, and properties. Well, I remember that inductive reason was just based off of patterns, whereas the facts should have been your deductive reasoning. So deductive reasoning is based off of those definitions, facts, and properties that you have. Let's see. A blank is a case in which a conjecture is not true. So a counterexample would be a case in which the conjecture is not true, and we form a conjecture based off of patterns for inductive reasoning. Okay? And in inductive reasoning, they're going to have some sort of pattern given to you for your first type of problems, and you're going to have to figure out from there what the pattern is and name the next two. So let's see, let's click on a little different marker here. If I had like 1, 1, 2, 3, 5, 8, and there's a pattern here that we could figure out. The next terms, for instance, would be 13, and the next one from that would be 21. So can you figure out the pattern? Well, the pattern is that they're adding the two numbers in front to get the next number. So they're adding the 1 and the 2 to get the 3, the 2 and the 3 to get 5, and so on and so forth. So hopefully you picked up on that pattern. I'll move on here, get a new colorful page right here, and other things. You only need one counterexample to prove a conjecture true. So let's see. Determine the conjecture is true. If not, find a counterexample. And this one says all whole numbers are natural numbers. Okay, well, most of the whole numbers are natural numbers, except for whole numbers includes one more thing. So a counterexample to this would just be the 0, because a 0 would be a whole number, but it's not a natural number. So that's the only logical example that we could find right there. Okay, looks like we're ready to start talking about what a conditional is, and of course the ways to rewrite a conditional based off the inverse, converse, or contrapositive. So let's talk about that real quick. All a conditional statement is another name for an if-then statement. So if Mr. Lane that's bad. If Mr. Lane could rap, you know I can, then he would be rapping. Alright, so we're supposed to write the, first off, I believe the inverse of this. So the inverse of this, no, we're going to write the converse first. So the converse just flips the flops the part that follows the if and the part that follows the then. So we're just going to again state it off. If Mr. Lane was rapping, then he could rap. Okay, so that would be the converse. Now the inverse of it just negates the original statement. So we'll put some just some knots in there, like if Mr. Lane cannot rap, then he would not be rapping. Makes sense? Alright, and the contrapositive flips and negates both. So in this situation we'll have if Mr. Lane is not rapping, then he cannot rap. Alright, very good. Let's go on and see what's coming up here next. Deductive reasoning. Remember, on deductive reasoning we have to have facts in order to show it with deductive reasoning, and that ties right into the proofs that come up a little bit later on, because all those facts that we learn and theorems that we learn, we turn around and write in proofs in the second half of this chapter. So let's just do one of these real quick. Well, those are kind of lengthy, but let's get the basics of inductive reasoning with a little bit of the laws. So, law of detachment. Been working on my writing, as you can tell here on this one. Just hard to do with the mouse. So, law of detachment. Well, remember, law of detachment says if P implies Q is true, then if given P, Q must be true. Okay, so that looks pretty good on that one. Now we're going to keep on moving here a little bit. Quite a bit to get into the section here. Well, we start dealing with some counter examples, and then some writing biconditionals. Remember your biconditionals? Both the converse and the original conditional statement must be true in order to write the biconditional, and it just uses the words if and only if. Okay, let's see, then the properties. So they'd give you an equation like m plus 2 equals 3, and you'd say given to begin, and then you'd use the subtraction property of equality to get x or m equals 1, and that would be just subtraction property of equality, and then we'd be done with that one. Okay, They do put some angle relationships at the end here. I'm going to show you one or two of these. So they got the line marked across here and something like that. So it's a linear pair that's formed. And then they're going to say this is z minus 2. And this is 2 plus 7z. Well, if these two form a linear pair, then they add up to equal 180. So all I'm going to do is add those two together, like z minus 2 plus 2 plus 7x. And then all we have to do is combine some like terms right here, which looks like those are going to add out. And then we'll have z plus 7. That should be a z and not an x. So I'm going to change that back to a z and change this back to a z. So 7 plus 7z, I'm going to go ahead and simplify that down to 8z. And we're just going to drop this other side all the way down to right there. Now we need to take and divide both sides by z for our last step. Alright, so z would equal, well, 8 will go into 18 2 times. That would leave us 16, 6 and 0. 8 times 5, 6, 7. Looks like 7.5 would be z. Alright, I'm going to go ahead and end this video. We didn't talk a whole lot about geometric proofs or flowchart proofs. Hopefully we talked about those in the last couple of days and you're still kind of refreshed on those. So, Mr. Lane signing out from OHS High School. Catch you on the flip side.